All right, let's go through this practice test. All right, on questions 1, 2, and 3, what we want to know is the first or second law of thermodynamics. First law of thermodynamics says you can't create or destroy energy. Second law of thermodynamics says anytime energy changes form, some of it gets converted to heat. In other words, entropy increases. So, the fact that a pendulum will eventually stop swinging is because it's converting energy to heat. That's the second law of thermodynamics. You get the same amount of work out of a machine that you put into it means that you cannot create or destroy energy. That'd be the first. And then a ball will never bounce as high, meaning that some of it got converted to heat, so it couldn't bounce as high. That's the second. If I said it can't bounce higher, that would be the first. All right, let's look at this next one here. We're going to match the example on the left with the energy transfer. Okay, snapping of a mousetrap is going to be B, because what we're doing is we're taking mechanical potential energy of a spring, converting it to kinetic energy. Number 5, an apple ripening on a tree, in which case light energy from the sun is being converted to the chemical energy in the sugars of the apple. Number 6, a person climbing a ladder. As they climb up the ladder, what they're doing is they're taking the chemical potential energy in their body and they're turning it into gravitational potential energy. Now you might be tempted to say, well, they're climbing up, don't they have kinetic energy? They do have some, but they're not really gaining kinetic energy unless they're going faster and faster and faster. But what they are gaining is gravitational potential energy because they're going higher and higher. Going faster and faster and faster. Instead, what's happening is friction is converting the energy to heat. If I lift it up in the air, it's being raised higher and higher and higher. It can fall. So anytime somebody's in a position where it can fall, it has potential energy. And when I let go of it, it falls down, giving it kinetic energy. Let me just move this up the page here. How do I do that? I go like this. Here we are. Okay. All right, so, well, number 10, I'm not going to go through. That's self-explanatory. Let's just try here. 11 through 13, I need to move this up again. Look at that great guy with the monobrow. Nice job, Samson. Okay, now notice, this is how hard he's pushing. This is how hard it weighs, and it weighs that in a downward direction. So, if the person pushes for 25 seconds, but the object never moves, so what I have is, I pushed with 220, it went 0 meters, therefore, I did 0 joules of work. I pushed on it, but I didn't transfer any energy to it. Now, number 12, if the person moves the object 12 meters and there's no friction, therefore I'm not converting it to heat, I'm converting it all to kinetic energy. I don't have to use the kinetic energy equation, I use the work equation because I know how hard the person pushed and I know how far the person pushed, so I just multiply their force times the distance and I get a work of 2640. Number 13 says if the moves at 12 meters, but friction causes it to gain this much heat. Well, however much, remember, first law of thermodynamics, however much heat it gained is how much kinetic energy it's not going to have. There goes my phone, let me pause. Okay, now let's see, our next one then. So the idea here is, and forgive me, I got distracted. So what we know now is that this many joules got converted to heat, so I have to take that away from the total, and that leaves me with this much here. If we had generated this much, then it wouldn't have gone anywhere. But that wouldn't make sense because if it didn't go anywhere, there wouldn't be any friction. Shut up, Eric. Okay, let's keep going here. All right. Whoops, what just happened? We're not getting what I want here. Whoops. All right. So for number 14, we want to know how fast. How fast is velocity? So I have to use the kinetic energy equation. I'm looking for the V. So what I have to do is substitute in. I know how much kinetic energy that goes here. I know, let's see, what the mass of it is, which is right here. And I'm solving for V. So in this case, I don't have to know the weight of it just yet. Now remember, when you're solving for this, don't forget when you're solving for V, you're going to have to take the square root of this number here divided by this here, and then you have to take the square root. Okay, let's see, now number 15. It says how far. To do far, that's a distance. I have to use the work equation because that's the one with distance in it. Now I'm going to take the kinetic energy and I'm going to use it for the amount of work because work is measured in joules. In this case, I have to use force, not mass, and I solve for that. Number 16, let's see, the question is, how much does the boulder weigh? Weigh is force, so I had to use the work equation, and I know that I have 17,000 joules of chemical potential energy to work with. I know I'm lifting it to a height of 12, so I simply divide this by 12 and get this. Simple machines work by trading force for distance. You go a greater distance using less force, as we're doing here with Mr. Vampire Man. Let's take a look at this. Okay. So, let's see here. Number 8, how much force would the person have to use? So what I have to remember here is that force times distance equals force times distance. Now with a lever, the distance I can use is from the fulcrum to where the force is applied. And remember, your hand inputs the energy into it. So the input is your force and the distance between your hand and the pivot. The output for our problems is always going to be the weight being lifted, and in this case the distance from the pivot to where the weight is force is applied to the weight. Now, let's see. So in this case, I'm going to substitute in. I want to know how much force the person has to use with their muscles. So I'll say unknown force times the distance of 1.4, the input, equals the output force times the output distance. And when I solve it, I get 85. Now the IMA is the input distance divided by the output distance. So in this case, the input distance is going to be from the person's hand to the pivot. So that goes on top as the input, and the output is from the output force to the pivot, and that goes down below, and that gives us an IMA of 4.2. Let's scroll up here, number 20. Alright, now I know what the IMA of the system is. So I'm told that the IMA is 4.0, and I'm told that you have to pull. So remember, you are the input, so that goes on top. The output is how high the object gets lifted, or how far do you lift it, so that's going to be down below. So remember to do this now, you're going to swap these two here. So I'm going to end up with 22 over 4 gives me 5.5. Alright, number 21. The question is, what is the length of the ramp surface? So I want to know how long is this ramp surface. Remember, with an inclined plane, this distance here is the input distance. The height is the output distance. Remember, output distance in our case is always going to be height. The weight of the object is the input force, and how hard you pull is the weight is the output, and how hard you pull is the input. So in this case, the question is, what is the length of the ramp surface? So that's going to be the input distance. So let's see, if you are using 26 newtons, that's you, times the distance you're going to move, equals the weight of the object, which is 120 newtons, times the height that gets lifted, and we solve it. It's a 10.2 meter long ramp. Number 22, a road is a simple machine, and it has an IMA. IMA is always found by taking the input distance, which is how far you go, divided by the output distance, which is how high you go. Since it climbs that high, that's going to be the output, and that gives us an IMA of 8.6. Alright, you'll definitely get something like this on the test, one of these tables. So the first thing you do is find the delta T. Remember, don't be afraid of the delta. It just means the change in the temperature. If the temperature started at 25 and up at 21, we have a delta T of 3.3 for the water, and we do the same thing for the metal, which was 3.4 and ended up at 21.9. I get 18.5. And notice that the ending temperature for both substances is always going to be the same in a calorimetry problem. So we have 24. Did energy flow into the water or did it flow out of the water? Well, the water was 25 and it ended up being 21. When the temperature goes down, that means energy is flowing out of it. That the energy that flowed out went into the metal and warmed the metal up. Now if I want to find, and this is what we always do, first we're going to find the delta Q of the water. So I use the heat equation, and I'm going to solve for the heat energy that changed for the water. So I take the mass of the water, which is right here. I take the delta T of the water and put it here for the delta T. The CP of water is 1, an easy thing to remember. That gives me 406 calories of energy left the water and went into the metal. Since I know where the energy went, I can then take these calories here. I can take the delta Q for the water, and I can then apply it to the metal. So I'm just going to take this here, I'm going to put it right over here and say, you know what? I'm going to use this heat equation for the metal this time. put the 406 calories here that went into the metal from the water. Now I'm saying that in this case the mass is the mass of the metal, 61.8. The delta T has to be the delta T of the metal, which was 18.5. And I'm going to solve for the CP of it. So that means I need to take 406, divide it by 61.8, then divide it by 18.5, and I get 0.36. And you know you've done it right if you get a CP that's less than 1. Remember, water has the highest CP, and it has a CP of 1. And let's keep going here. Oh, now we're getting into the nitty-gritty, aren't we? Okay, what we've got here is, what is the specific heat of lead? So I'm going to use the heat equation and solve it for specific heat capacity. So remember, delta Q has to be measured in calories, so the 60 calories goes here. Let's see, the mass has to be how many grams the object is. It's 100 grams. That goes here. Now I'm told it went from 20 to 0, so there's a 20-degree change. So the delta T is 20. So 60 divided by 100 divided by 20 gives me 0.03 calories per gram degree Celsius. Now in the next one it says, how much does the temperature go up? So in this case I'm solving for delta T. How much did the temperature change? So therefore I need to find how much energy went into the room, and that's going to be measured in calories. So I take this number here and put it here. And then the mass has to be the mass of the air in the room. And by the way, these are good numbers. These are real numbers. There's the mass of the air in the room. I'm solving for delta T, so I have to know what the CP of air is. And the CP of air is right here, which is pretty high, actually. It's about the same as aluminum. All right, and now I have to just basically take this number, divide it by 132,000, and then divide it by 0.237, and that gives me a delta T of 8.25 degrees Celsius. Now, you're definitely going to get a question like this next one on your test. I take two identical pans on two identical burners. One has 100 grams of oil, one has 100 grams of water. The only difference between these things is that one has the oil ends up much hotter than the water, and the only way I can explain that is to say it was easier to change the temperature of the oil because the oil has a lower CP. And by the way, everything has a lower CP than water, so that kind of makes it easy. Alright, let's look at number 30 here. I wanted the IMA of each pulley system shown, and look, I already made a mistake to start off with. Okay, here we go. Alright, what you do is you count the strings. How many strings are getting shorter? So let's look at A. I have two strings that are going to get shorter, and since I'm trying to lift this upwards, this rope here is helping, so that gives me 3 strings. The 2 that are getting shortened, and the one that's lifting is lifting in the same direction as one I'm trying to pull up, so that counts. Now let's look at the second one here. I am pulling down on this one, so that doesn't count. There's only one string getting shorter. I have an IMA of 1. Not going to make work any easier. On C, when I pull down on it, that's the opposite direction from the way this object is moving, so I'm not going to cancel that. I'm not going to count that one. That leaves me with 2 strings that are getting shorter. The IMA is 2. Now look at D. Whoo-wee, that's a busy one. Alright, I'm lifting up in the same direction that this is being pulled, so this one counts. That gives me 1, 2, 3, 4. I have an IMA of 5. Well, I don't know how much I have to do for you on this one here. There's really not much to explain. Look at your notes. Read what I got here. This is basically, these energy sources here are things you can read about and associate them here. There's no magic there. Problems with fossil fuels, we're going to run out of them. They cause air pollution. They kill people from cancer and respiratory distress. Carbon dioxide is the big problem that causes climate change and is making the oceans become acidic. Let's see what else we got here. Fossil fuels disrupt the carbon cycle. What happens to the carbon cycle normally is this. The amount of let's how do I do this? Normally what happens is you have a certain amount of carbon dioxide given off by animals as they breathe, and that same amount of carbon dioxide is taken in by trees as they undergo photosynthesis. But what we're doing now is we're dumping a bunch of carbon dioxide into the atmosphere. So more CO2 is going to the atmosphere than the plants take out of it. That's disrupting the equilibrium and causing more carbon dioxide to end up in our atmosphere. And basically, number 34, you can tell something's running backwards if you see that entropy is decreasing, because entropy doesn't normally decrease, it increases. So anytime you see something getting messier, your brain, or melting, whatever, your brain says okay. But if you see disorder turning into order, something's wrong. Now, to do number 35, let's just look what we got here. Last one here, we're done. Remember, big C calories, those are dietary calories. It takes 1,000 regular calories to equal one of these, so you always, to do a conversion, you simply start off with what you've been told, 450 calories. I don't want big C calories, so I put them in the basement. One big C calorie equals 1,000 little C calories. So what I can do now is I say, well, calories are gone. Now I have little C calories. So then I say, well, I'm going to put my little C calories in the basement, and one little C calorie equals 4.2 joules, so the calories are gone. And then what that does is that leaves me with 450 times 1,000 times 4.2 gives me 1,890,000 joules. So then on B it says how high. Now how high is distance? I have to use the work equation. And so work is measured in joules, which I have here. So 1,890,000 joules goes here. Naughty me, I should have put a J there. Sorry about that. Equals how the weight of the person is measured in newtons. And I just have to solve it for D. And when I do that, I get 2398 meters, which, by the way, is 8 times the height of the Empire State Building. That's one cheeseburger. Think about it next time you go to McDonald's, and that's it for this. Good luck on the test. Please study.